Okay. Alright, so last time I mentioned that the way we're doing it, the hardest thing about finding probabilities, at least in the problems we're dealing with, is finding out what that event space and sample space should be. Because once you have them, it's just a matter of stacking them in a fraction and then getting that fraction as a percentage or a decimal or whatever's required for the problem. So that's definitely the easy part. So the harder part is finding out what is the size of the sample space, what is the size of the event space. And we're just going to talk about some counting techniques, literally counting techniques for finding out how big an event space or a sample space is. So we have some formulas actually coming at the end. There's going to be a principle that we've already discussed. It's called the fundamental counting principle, which is something I already mentioned last lecture, but I'll go into a little bit more detail here. We'll do some examples. Then we'll look at, in those examples, some techniques, just making more use of the fundamental counting principle in different contexts. And then we'll look at two formulas for combinations and permutations, which are some super useful ways to count things. And actually, there's even a button on your calculator for both of those calculations. So we'll talk about that. Okay, so first you see in the notes the fundamental counting principle. Is just a way to tell us the total number of possible outcomes in a sequence of experiments. And what it is the product of the number of possibilities in each individual experiment. So we've already talked about this, but just as an example, I'll start off with example 1 because you may be thinking, like, what the heck is that saying? But the key word there is product, which means we're using the operation of multiplication. So example 1 says you're at a buffet where there are 6 options for protein, so that's like meats or like beans or whatever, protein. 3 options for vegetables and 5 options for fruit. If you get one of each on your plate, how many possible plates could you make? Or how many possible choices do you have for one plate? How many possible choices do we have? So the fundamental counting principle tells us that if we take the product of the number of possibilities for each individual piece of this problem, then we take the product of those numbers, then we'll end up with the total number of possible outcomes for the experiment as a whole. And this is, I don't know if I'd call example 1 really an experiment. It's just counting up number of possibilities for a plate at a buffet, right? But experiment's a general term. So one technique is to draw little blank marks, little blank spots representing each option here. So the first slot is representing the 6 options for the proteins. So I would write a 6 there, representing the 6 different options in that first category of this experiment. The second one is there are 3 options for vegetables. So this is the number of possibilities in each of these categories: proteins, vegetables, and then fruit. And that's it, right? And what you do is you take the product of them. So just pop that into the calculator and we're going to get 90 possibilities. Whoops, 90 possibilities. Now if you really want to know how this is working, we can make something called a tree diagram. So consider, let's do this. I'll even use colors here. Oh no, is this going to get confusing? Maybe I won't use colors. It might get to be too much to write down or too much to keep track of. So consider the first spot where there are 6, 1, 2, 3, 4, 5, 6 possibilities for proteins. Yes, I will use color. Okay, then off of each of those 6, there are 3 possibilities. There are 3 possibilities from each protein for vegetables. So maybe it's like meatloaf and then, I don't know, green beans, lima beans, or spinach. And there's going to be 3 for each one of these, right? So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. All right. So this is, and I'll use some color in between that's arbitrary. So those 3 for that one, 3 for that one, 3 for that one. Okay, so already just based off of these 2 categories, you're seeing 18 possible combinations. 1, 2, 3, 4, 5, 6. Basically just counting up the number of dots at the end here, right? Now at the end of each of these vegetable possibilities, these little green dots, there are 5 options for fruit. So off of every single one of these little green dots, I need to draw 5, 1, 2, 3, 4, 5 possibilities for fruit. And this is going to get too much to write down. 4, 5. I'll try and maybe stack them. I'll just do 1 so you get the idea. 1 off of 1 of these proteins. So here, off of every single one of these, I'm getting 5. Right, and I'm going to stop here because my picture is going to get too complicated. But you can see if I listed every single one of these little purple dots and I counted up all the purple dots, there would be 90, right? There would be 90 because there would be 5, 10. So each one of these has 5, right? 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 85. I skipped something. It's 75, 80, or 85, 90. I messed up somewhere. I miscounted. But it would end up being 90. Okay, so this is, if I completed this, if I had more room and I really spread it out, this would be called a tree diagram. But it's basically just saying, take the product of all of them, right? That's all it's saying. Okay, or that's just a picture representation of taking the product of these 3 numbers. Let's move to example 2 now. Yeah, these problems are more fun. Example 2. So we're creating a password. Oh, hang on. All right. We're creating a password. We want to make a new password that contains 5 letters followed by 3 numbers. How many possible passwords could you choose from? Okay. 5 letters formed by 3 numbers. So we have a fixed length for our password, right? Isn't it 8? There's going to be 8 positions in our password. 5 letters followed by 3 numbers. Okay, so we're not getting into symbols or anything like that. We're not worrying about whether the letters are capitalized or nothing like that. It's just 5 letters, 3 numbers. So, if I use this technique writing a little slot for each letter and then a little slot for each number, how many letters do I have to choose from in the first position? Well, A through Z, right? So 26. This is representing the number of options for the first position. And why is it 26? Because it's a letter, which is a, well, we should specify an English alphabet letter. I'm not familiar with any other alphabets, but I'm pretty sure they don't all have just 26, right? Some have more, I'm sure. So this is, we're talking about the English alphabet, right? Alright, so now how about for the second position? How many letters do I have to choose from? Well, still 26, right? Because they can be the same, so it'd still be 26. 26, in fact, the first 5 would be 26. Okay, so 5 letters. And then what about numbers? What about numbers? How many digits are there to choose from, assuming we're using the base 10 system and not like hexadecimal or something weird like that? Well, there's 0 and then 1 through 9. So there are 10 possibilities. Okay, so this is representing I'm just going to shorthand this and say representing the number of digits to choose from, which is 0 through 9, right? So these are all A through Z, A through Z, A through Z, A through Z, and then this is 0 through 9, 0 through 9, 0 through 9. All right, and we just, how do we figure out how many possibilities this is altogether? You just take the product, right? So this is going to be some ginormous number. The cleanest way to write this would be 26 to the 5th power, because there are 5, times 10 to the 3rd power. That would be the cleanest way of writing it. We could also just multiply it out, figure out what it is, but it would be a giant number. So this is really the most concise way to write it. Alright, so example 3 is similar. Example 3 says that we are making a password similar to the previous example, but you don't want to repeat any letters or numbers. Okay, so how many possibilities are there? So we have the same password, in other words, it's 4, 5, 6, 7, 8. But this time we don't want to repeat any letters. So in the first, or numbers. So in the first position we have 26 options. But now we've picked a letter here. Just some random letter, A through Z. It could be like K, L, whatever. Just some letter. But then how many options do we have here? If we don't want to repeat, then we've now taken our options down by 1, right? So this would be 25. Similarly, now we've used 2 letters, so now the next spot would be 24 available letters, and then 23 available letters, and then where are we at? 22 available letters. Now we're getting into the numbers. So this spot has 22 available letters because 4 have been used back here, and we don't want to have any repetitions in this example. In the example 2, we didn't care about repetition. So now for numbers, it's going to go similarly. We start off with 10, then 9, then 8. Okay. Not a clean way of writing this. Not really a clean way of writing this. We can just pop it into the calculator and kind of let's get a feel for, you know, at first let me figure out what the previous one was, just so we have an idea of how many. Yeah, it's like an insane number. So this first one is 11,881,376,000. And this one is 26 times 25 times 24 times 23 times 22 times 10 times 9 times 8. It's much less. It's 5,683,392,000. So half, roughly. So just by saying I don't want any repetition in my password, I cut the number of passwords down by half. I mean, it's still a giant, 5 billion, right? That's still a giant number, 5.5 billion. Okay, so let's look at example 4. How many possible 4-digit numbers are there to choose from when making a PIN number, so like a bank PIN number, if the first digit cannot be a 0? The first digit cannot be a 0. So 4 digits, so I'm going to put 4 slots. And I'm talking about numbers, digits, so I'm thinking the number 10 is going to be all the options, right? But the first digit cannot be a 0. So that means how many possibilities do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9 possibilities, cannot be a 0. But then here, I can have a 0 and any other digit, and I can have any other digit in any of those other spots. I'm not worried about repetition, so I don't need to make these drop, right? The only restriction on this is that I cannot have a 0 in the first spot. So what I'm doing here, if I was to represent this as a tree diagram, is in the first spot I've got 1, 2, 3, 4, 5, or 6, 7, 8, or 9, but not a 0. And then off of each of these, I'm having a 0, a 1, 2, 3, all the way down to 10 for each of these, right? And then off of each of these, I'm having 10 more. And then off of each of those, I'm having 10 more. So in other words, making a tree diagram in this case would obviously be still way too big, because there would be 9,000 options. Excuse me. There would be 9,000 options. Okay. I think these are kind of fun. I don't know. Maybe not. 5. How many possible 4-digit numbers are there to choose from when making a PIN number? Okay, so 4 digits, so let's just start with that again. If the first, where am I? If the first digit is a 7 and the last digit is a 9 or a 5. Okay, so I know that my first digit is a 7 and the last one is a 9 or a 5. But I'm not going to write a 7 here. Right? I'm going to write a 1. You see why that's true, or why that's appropriate here. I'm keeping track in this little diagram of how many options there are in each slot, not what the actual number is. Right? So how many options are there in the first slot? Well, just 1, because I know it's fixed at 7. If you'd like, you can have a little diagram off on the side that is the actual possible digits over here, and it would be 7 blank blank and then a 5, or maybe 7 blank blank 9, because it says it ends in a 5 or a 9, right? Yes. And of course, these could be any digit, 0 through 9, 0 through 9. But you see, when I'm writing this, I'm keeping track of how many options there are in this slot. And if it has to be a 7, then there's 1 option. And at the back, how many options are there? Well, if it's a 5 or a 9, that's only 2 numbers. And these middle 2 digits have 10 options. Okay, so taking the product of all of these, I'm getting 200 possibilities. So you see what I mean about keeping track of, there's 2 separate things going on here and here. This is keeping track of the number of options. This is keeping track of what the actual numbers might look like. So for example, I could have 7005 or 7019. You know, these are just 2 examples out of this 200. Okay. It's important to make note of that, because if you were to write a 7 here, you would end up accidentally multiplying by 7, possibly, and that would completely throw off your answer. Example 6. How many ways are there to arrange the letters in the word history? So we have the word history, and we're asking, given those letters, how many different ways can we rearrange them to make just new word, well, probably not a new word, but just rearrangements of those letters. Well, the word history has 7 letters. Right? 1, 2, 3, 4, 5, 6, 7. 7 letters. Okay. If we were going to rearrange them, if I'm following this little technique with these slots, if I'm picking the first letter, I have 7 options. Could be an H, could be an I, could be an S, T, O, R, or Y. Right? 7 options. Now I've picked one. It could be I, it could be Y, it could be a T. But the point is, 1 is taken here. So how many options do I have here? There are 6. Now that 2 are taken, the next option, or the next slot, is going to have 5 options. So maybe I've used the I, the S, and the T. So now this position can only choose from 4 letters, the H, O, R, or Y, just as a distinct example. So I think you get the picture here. It's going to go like that. So the last spot will not have any options. Alright. First spot has 7, and then it just decreases by 1 because we're using a letter up each time. And what is this? What is this? Does my calculator have a factorial button? Yes. Let me say not possibilities, but arrangements, because that's what they wanted. Arrangements of those letters. So this is actually a multiplying, it's picking a number to start at, like 7, and multiplying it by numbers that are decreasing by 1 each time and ending at 1 is actually a special calculation called a factorial. So I can say we just made use, maybe without knowing it, of a special computation operation called a factorial. You probably have this button on your calculator. N factorial, so n just being some arbitrary number and then an exclamation point, n factorial is equal to the number n times the number n minus 1. So if this is 7, then this would be 6, and then n minus 2, etc., all the way down. Well, how do I want to say? Oh, it just all the way down until you get to 1. All the way down till you get to 1. So for example, 13 factorial is equal to 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times, and then I ran out of room, so I'll bring it down here, 5 times 4 times 3 times 2 times 1. And you may say, gosh, this would suck to plug into a calculator just because it takes so long, and you might miss a number, right, having to punch all those numbers in. But note, this is a button on your calculator. It should be anyways, if you have a scientific calculator. There's some way to get your calculator to do it if you have a scientific calculator. So if I wanted to know what 13 factorial is, I don't have to do all of this. I can just say 13 and then find that little button with an N and an exclamation point, and I get 6,227,000,000, whatever. I don't really care too much what it is. The point is, I'm telling you there's a button that does this for you. Now, you may not know that a problem is calling for a factorial operation until you kind of write it down. But then once you have it written down and you say, oh, this is just 7 factorial, at that point you then tell your calculator you just do 7 and then the factorial button to get the answer. But it may not be obvious right away that you're going to be doing a factorial operation in a problem until you write down the little, until you write down the options, and then it becomes clear that's what's going on. Because sometimes you have that behavior where each time it's decreasing by 1, but it may not be a full-on factorial. Like in example 3, with the letters and the numbers decreasing by 1 each time, but it doesn't, this would not be 26 factorial because it stops at 22. So this kind of has to be calculated, just the manual way, just plugging in each of these numbers, because you can't take any shortcuts with a factorial here because it's missing like most of the rest of the factorial. Okay. So example 7 is just practice with this factorial thing. I just want to show you how fractions of factorials work, because that's actually going to be a really important technique for you to know, or for you to have for the last part of this lecture, which is all about these 2 new formulas. So example 7 just says to simplify 18 factorial over 16 factorial. Now really quickly, I can tell you that this is just going to be 18 times 17. See if you can figure that out. Like without plugging in, without plugging these into the calculator and then dividing, do you see why it's just 18 times 17? In the bottom, aren't you going to have 16 times 15 times 14 times all the way down to 3, 2, 1? And in the top, aren't you going to have the exact same thing except with those extra 18 and 17? Because 18 factorial has 18 times 17, and then it has that 16 factorial built into it. Right? Of course it does, because it's a bigger number. And since this is all connected with multiplication, all of these numbers are just going to cancel out. Everything in between is going to cancel. All these numbers are going to cancel. Of course, the ones don't really matter. They're not really doing anything, right? But so we can say they cancel, and we're just left with 18 times 17, which of course is super easy to calculate, much easier than all of this. Okay. So that's kind of the point with fractions of factorials. Should cancel nicely. Should clean up nicely. Okay. Oops, nicely. Okay, let's talk about these two formulas, combinations and permutations, which you see in the lecture notes. So these maybe kind of scary looking formulas, but they're really not that bad. A combination, so in the context of counting things, so I don't mean combination in just the typical sense of the word, this is now meaning something different in this class. How do I word it? I want to word it a little differently, a little less technically, maybe. Well, yeah, that's not bad. A combination calculation tells us, because it's a calculation, it's like a formula, tells us how many ways there are to select R number, so that's going to be some number like 5 or something, some number that's given in the problem, R number of objects from a group of n objects. So maybe we want to select 2 things out of 5. Then that calculation would be a combination calculation, which I haven't even written down the formula yet. I want to say a couple more things that are important here. Each chosen object so this is only for problems where each chosen object is used only once, and order does not matter. So we're not worried about the order of objects here. In other words, we're not like ranking things. Like this is for like maybe choosing a group of people. So say you have like 20 people and you want to choose 2 people to represent the committee, but there's no order to those 2 positions. It's not like president and vice president or first spot and second spot. It's just 2 spots and they're not ranked. Order does not matter. That's what this would be for. Now the calculation goes, so I mentioned these 2 numbers, n and r. Those are the only 2 numbers involved in this calculation, just 2 numbers. And it is going to be n factorial, so the number of objects in the group itself, factorial, over r factorial, so the number of objects chosen, and also in the bottom, so times n minus r factorial. And it's denoted two different ways. It might, on your calculator, you might see this. It's like parentheses. It almost looks like a fraction, but there's no fraction bar. NR, or NCR, like that. And I'm not completely sure how everyone's calculator is going to handle that. Everyone's calculator is a little different. I think with mine, the way I had to do it is I would type the n number first. So let's say I wanted to do 7CR, or 7 choose R. Sometimes this is called a choice function, or like choosing a number of objects out of a larger group. So sometimes it's read as n choose R. I'll write that down. N choose R. So if I wanted to do like 7 choose 5, in my calculator, the one I have, you would have to hit the number 7, then this button, and then the number 5, and then equals. But everyone's calculator is going to be a little different. What would that be, by the way? Oh, dang it. What is 7 choose 5? Well, it would be, according to this, 7 factorial over 5 factorial times what's n minus r. 7 minus 5 is 2 factorial. So don't forget that every number in this should have a factorial on it. After you do the subtraction, that number should have a factorial too. So this is going to give me 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1, that's 5 factorial, then times, because the operation in between these two is multiplication. 2 factorial is just 2 times 1. Now you notice all of these cancel with all of these, and I'm essentially just left with 7 times 6 over 2, because this 1 doesn't matter, which is just 42 over 2, so I'm getting 21. So this might answer a question like, how many ways are there to choose 5 people out of a group of 7, where the order of that group of 5 does not matter? There would be 21 choices. There would be 21 choices. Okay. So look at example 9. Let's look at example 9, going a little out of order. We'll keep talking about combinations and then we'll come back to permutations. Example 9 says, the number of ways 5 people can be chosen for a committee from a group of 120 employees is given by which of those two calculations? Well, so I want to change this question a little bit and say, how many, because I've kind of already given away that it would be a combination. How many ways are there to choose 5 people So it's implied that order does not matter here. If it's just a committee, the committee's not ranked. There's not different ranked positions in the committee. It's just 5 people. We just need 5 representatives from this group of 120. And of course, each person can only be chosen once, right? One person cannot take the spot of 2 people, right? So N is going to be the large group, and R is going to be the size of the smaller subset we want. So we would say 120 choose 5 is going to be equal to 120 factorial over 5 factorial times the difference of these factorial, so 115. Okay. Now, this would be insane to write out, right? So instead, I'm going to be clever about this and say, I don't need the 150 in the top. I'm not going to need 115 or 114 or anything below, because they're all going to cancel. So in the top, I'm just going to have 120 times 119, 118, 7, and that's it. Because the 115s and below canceled with this one right here. Now in the bottom, I still have that 5 factorial to deal with. So somehow I've got to figure out how these will cancel with some of these. Okay, so now we've got to be able to flex our, fraction simplification techniques. Like, for instance, I know, 5 and 4 are 20, and surely 20 goes into this. In fact, what is 5 times 4 times 3 times 2? Well, that's 20 times 3 is 60 times 2 is 120. So actually, very nicely, all 4 of these cancel with this first term. It usually isn't that easy, but that's pretty nice. And of course, this 1 doesn't matter. So now I'm just left with these 4 numbers. And that needs to be punched into the calculator. 119 times 118 times 117 times 116 is 190 million. Okay. So we still haven't started talking about probabilities again, but that's okay because this section is mainly just about counting things. One example, though, of how this could be useful in the real world is, say you work for some company that has 120 members and they want to pull 5 people to represent this company. And let's just make this hypothetical super easy to understand. Let's say that there are 60 men and 60 women, so split right down the middle. And so we want the committee to be representative of that. So we either want 2 men, 3 women, or 3 men and 2 women, just to have a good representation, right? So let's say the group ends up having 5 men. Your company, and the people are supposed to be chosen randomly, but someone had to make the choice of who to choose, right? So 5 men are chosen. And now your company's saying, one of the, the women half of the group is saying, well, that's not right. In fact, that's so not right that we think there's something nefarious going on. And the company's going to want to claim, no, it was just an accident, we'll fix it, the chances of this happening were actually pretty high. But you could calculate, based off of these techniques, not this exact calculation, but very similar techniques, you could calculate the probability of selecting 5 men, just 5 men from a group of, of both men and women. And you could see how high is that probability. And if it's a really low probability, then you may say, you know what, no, there was something nefarious going on. You guys chose men on purpose, excluding the women. Or maybe the probability is a bit higher than you thought, and you'd say, oh, okay, it was just an accident, but let's get the committee fixed and get equal representation. Okay, so I paused for a second and thought about how that calculation would actually go, and I think it's going to be easy enough for us to actually do. So let's run with that problem I just kind of came up with. So let's say based off of this example 9 that I've written here, there are 60 men and 60 women in the group of 120. The committee chooses, the committee is chosen and ends up having 5 men. Okay. What is the probability of this happening? Because if it's a very low probability, then what would that imply? That would imply that it was done on purpose, right? If it's very low probability that it would happen on its own randomly, then someone had to make that decision. Okay, what is the probability of this? Now, we already have our sample space. It was the calculation we just did. This is the total number of ways that we can select 5 people from a group of 120. 190 million. So remember, probability just boils down to event space divided by sample space. But we've already got our sample space, which I'd like to write very cleanly just as that 120C5. We'll replace it with its actual computation in a second. What would the nice clean version of event space be here? Well, the number of ways that there are to have 5 men in the committee. So how could we calculate that? How many ways would there to be? How many ways are there to pick just 5 men? Okay, so the way we can count the event space is we can think about it as, the question is, how many ways are there to get a committee of just 5 men? So isn't that kind of the same as saying, how many ways are there to choose 5 people from this group of 60? Right? Because that's half of the group. So it's like 60 choose 5. So we're trying to calculate the probability of just picking the entire committee just from that half of the population. So this event space, the size of this event, I should really say size of event space, size of sample space here, right? But that was kind of implied. So the number of ways to choose 5 people from just half of the population, that's why it's 60 there. And by the way, that is going to give us these 2 numbers. First of all, we already know this calculation to be this. And the top calculation, let's see, 60 choose 5 is 5,461,512. Let me redo that. I want to make sure I got that right. So 60 times, where's my calculator? 60 times 59 times 58 times 56, stopping there because I would not need anything below 55, and then I would divide by 5 factorial, which is 120, so divided by 120. Well, I got something different this time. Let me try it again. 60 times 59 times 58 times 57 times 56. I think I missed 57, then divided by 120. Yeah, okay, I got the same thing. I just didn't multiply by 57. Okay. So this is my fraction, and what the heck is this as a percentage? Well, I would just divide this by this, so divided by 190,578,024 equals, and then times 100 to make it a percent, and I'm getting a 2.86, we'll just say 2.9% chance of selecting all men for the committee. So it seems a little bit suspicious, right? If all the men are chosen, if all the people on the committee are chosen and they're all men, then there's only a 3% chance of that happening, roughly. That's pretty low chances, right? So I would think, that's a little bit shady. Okay, cool. So that's how this can be applied to real life. Now we still need to talk about permutations. It's very similar computation. It's just it's just used for a different type of problem. So a combination told us how many ways there are to select R number of objects from a group of n objects, which is exactly what a permutation is for, except for that last stipulation, which is that each chosen object for a combination is used only once, and order does not matter. That's the key difference here. So this is for like ranked positions where order does matter. Where order does matter. So for instance, oh well, I need to tell you what it looks like first. It's denoted as subscript n, then capital P, then subscript r, and it's just going to be n factorial over n minus r factorial. So it's very similar. Very similar, and we don't have that other notation like for combination with the little parentheses. That's specific just for combinations. Okay, so it's very similar, just without that r factorial in the bottom. So since we're dividing by less, that means this number should be bigger than it would over here with the same r and n. Because order does matter, that means we're going to get more possibilities from this. Okay, so for example, well, let me run you through a computation first. 8p6 would be 8 factorial over 8 minus 6 factorial, so that's going to be 2 factorial. And that's going to give us 8 times 7 times 6 times 5 times 4 times 3, right? Because the times 2 times 1 would cancel. And what is that going to give us? But you should have buttons on your calculator for this, by the way. I'm using a desktop calculator, and I don't think it does. Okay, 76543. I'm getting 20,000, so I'm having to do these by hand. Probably would have been easier to just do 8 factorial and then divide it by 2, but anyways, that's how the calculation works. So let's do an example of when this is useful. So going back now to example 8, which says, consider a race with 140 participants. The number of possible outcomes for the top 3 positions is given by this or this. I want to change it again. I'm going to say, how many possibilities are there for choosing 3 people Now, if I left it just like this, it would be a combination problem. But the point is, they say the top 3 positions. That implies that there's an order to them, like first, second, third. So order is going to matter here. Because if I have Jeff, John, and Daryl, there's a bunch of different combinations for having those 3 in my choice, right? Could be first, second, third, or it could be second, first, third, or third, first, second, or, you know, all different first, third, second. Oh, no, I already said that. Anyways, different combinations, right? So what I need to do here when I reword this is make sure it's noted that these are ranked positions. So as I've written it right now, that's not implied. So I need to add something here. How many possibilities are there for choosing 3 people from a group of 140 if the positions are ranked? So this is a little bit more explicit the way I've written it. In the problem, as it's stated in the notes, it's a little bit less explicit, it's more implied, because it says the top 3 positions. So you have to, from the context of how that's written there, you have to understand, you have to assume that those positions are ranked if they're the top 3. Because having a top 3 implies that there's, that there's order to this list. Okay, so once we understand that they're ranked, we're choosing 3 people from 140. The calculation is going to go like this. We're going to have 140 factorial over the difference of these factorialed. And remember, this is going to cancel nicely. The 137 and below is going to disappear, so I'm just going to have 140 times 139 times 138, which I've run out of room there. And that's going to give me 140 times 139 times 138. 2,685,480 possibilities. It's a lot. If you've ever considered, or if you've ever seen like I know Alabama doesn't have a lottery, but if you've ever heard someone explain like how low the chances are of you winning like a jackpot lottery, it's these kind of simple calculations that can get you to those numbers like that. Like, oh, if everyone plays this, or if a certain number of people play this jackpot and they're only choosing one person to win, then your chances of winning are super low. Like maybe if 140 people played and they only choose one winner, then what would that look like? It would be 140 divided by 140 factorial divided by 139 factorial, which would be, wait, is that what I meant to say? Oh yeah, that would only be 140. Duh. Yeah. Anyways, of course, the number of people who play the lottery is a lot more than 140, which is going to decrease your chances. Okay. I don't know how the lottery works. I shouldn't have used that as an example. Okay, so this is it. Make sure you look at these problems. This is a section where you really just got to do a lot of practice. It's not super heavy, and it's like it's not really abstract. You've got a couple new formulas to work out. Once you do a few of these problems with permutations and combinations, so you see the difference between how the problems are set up, then it'll seem easier. So make sure you do all those problems that I've listed in the bottom of these lecture notes.